All right, welcome to video 3, introducing Ramsey theory for graphs. My focus in this video is going to be on a general bound that we're going to try and prove for all classical Ramsey numbers. And at the end of this video, I'll also take a little bit of time to talk about some ways that you can go about generalizing the concept of a Ramsey number, and then why these actually are considered the classical case. So far what we've done is we've looked in our previous videos at how a Ramsey number is defined, and we've proven a couple of different values of them. We looked at R of 1t and R of 2t. These are the ones that we usually consider the trivial Ramsey numbers. They're pretty straightforward to evaluate. But then we stepped it up a little bit and went through and mathematically argued the values of R of 3,3, R of 3,4, and R of 4,4. At the current time, this is a complete list of the known classical Ramsey numbers. If you're ever curious about what's known on this topic, take a look at Radzikowski's dynamic survey. It's freely available in the Electronic Journal of Combinatorics. Every couple of years, Radzikowski will update it, and basically it, for the most part, it contains the current state of knowledge on the subject. And as far as I know, the last update was in 2017. As far as I know, this is the current state of what we know in these classical values. Now, whenever we can't get exact evaluations, like the cases that are up here, we can often find some ranges of values. And of course, the goal is to ultimately narrow those ranges down until we can eventually evaluate these numbers. So for example, R of 5,5 is known to be between 43 and 48, and R of 6,6 is known to be between 102 and 165. So as the arguments get bigger, the ranges in general tend to get bigger as well. Now, one property I didn't mention in my last videos, but I feel like I shouldn't neglect it, is a property that may seem somewhat obvious, but it's the fact that R of ST is always equal to R of TS. We can switch the order of the arguments. On one hand, the way to think about it is it doesn't really matter what we call our colors. I can call the colors red and blue or blue and red. It's just a name. It doesn't really make a difference. But you can also give a more rigorous argument as to why this is the case. If you were to assume that, say, R of TS was strictly greater than R of ST, well, what that means is that we can find a two-coloring of a complete graph with this many vertices minus 1 that lacks a blue KT, or sorry, a red KT, and lacks a blue KS. Take that coloring, switch all the colors. You then create something with one less than this number that lacks the red KS and the blue KT, making it to where this number isn't less than that one to begin with. So you can go through and give a more careful argument there using the definition. So my main focus in this video is going to be on proving an upper bound for the Ramsey number R of ST that is due to Greenwood and Gleason. And this really falls as a special case of Ramsey's theorem. Of course, at the time that Greenwood and Gleason wrote their paper in 1955, they weren't familiar with Ramsey's work, so they were working from the ground up. So let's take a look at their theorem. Greenwood and Gleason proved this in 1955. What they proved is for all S and T bigger than or equal to 2, the Ramsey number R of ST is less than or equal to R of S minus 1t plus R of S T minus 1. And you'll find in some books they refer to this as Ramsey's theorem just because it is really a special case of Ramsey's theorem, which basically states that Ramsey numbers exist. This is a little bit more than just that. We're getting an explicit upper bound for what this Ramsey number is. So I really think this should be credited more to Greenwood and Gleason. So let's take a look at the proof. I'm going to go ahead and let P equal to this number, R of S minus 1t plus R of S T minus 1. And we're going to consider a red-blue coloring of K sub P. And we want to try and argue that we're guaranteed to force either a red KS or a blue KT. And then if that happens, we'll know that this Ramsey number is less than or equal to KP, and then we just plug in what P is. So we'll consider red-blue coloring of the edges of KP. And let's look at two separate cases. So case one is the case where there exists a vertex U that is incident with at least R of S minus 1t red edges. So without loss of generality, I'm going to assume that UA1 all the way up to U sub R sub S minus 1t, that is my collection of red edges. So without loss of generality, let's assume that UA1, UA2, all the way down to UA R sub S minus 1t, but all of these are red edges. Well, if we were to focus now on the subgraph that's induced by A1 up through A sub RS minus 1t, that complete graph has this many vertices. Therefore, it's either going to contain a red KS minus 1 or a blue KT. If it has the blue KT, we're done, because that's all that we're trying to argue here. Otherwise, it's going to have the red KS minus 1, and then the last key is to go ahead and include the vertex U, because it connects with all of those via red edges, and that will form our red KS. So let me make that a little more concrete here. The subgraph induced by the set A1, A2 down to A, R, S minus 1t contains a red KS minus 1 or a blue KT. In the latter case, the case where we have the blue KT, we're done. Otherwise, there exists a red KS minus 1, and then if we go ahead and include the vertex view, that will form a red KS. And that does it for that case. So we've proved that anytime we have a vertex that is incident with at least R of S minus 1t, anytime it's incident with at least that many red edges, we're guaranteed to have one of the complete monochromatic subgraphs that we're looking for. Let's take a look at the second case. Basically, our second case is just everything that's not in this case. So that's case 1. Let's take a look at case 2. I'm going to keep this first assumption up here. All right, case 2. Well, if we don't have at least R of S minus 1t edges that are red connecting to some vertex, then every vertex has at most that many minus 1 red edges. So every vertex is incident with at most R of S minus 1 T red edges. Well, let's think about what the degree overall, like if you can include all red and all blue edges, we're looking at a KP, which means there's going to be P minus 1 edges coming out of it. If we have at most this many, sorry, minus 1, I said one thing and wrote something else. If we have at most this many red coming out of any one, then we have at least P minus 1 minus this blue edges. So every vertex incident with at least P minus 1 minus R of S minus 1 T minus 1 blue edges. Notice I can cancel the ones. And if I look at what P is equal to, well, P is this sum. So now I'm just subtracting R of S minus 1 T from that sum. I'm going to get rid of my ones. And what's left over is this one. And at this point, the argument's almost the same as the first case. We're just switching the rules of red and blue. So without loss of generality, let's go ahead and assume, this time I'm going to use vertex V, and then V1, V, V2, all the way down to VB, RS, T minus 1. Let's assume these are blue. And of course, the subgraph induced by the set of B1 up through B, RS, T minus 1. Contains a red KS or a blue KT minus 1. Well, in the former case this time we're done because we have our red KS. In the latter case, we just now have to include the vertex V, and that forms our blue KT. So in the former case, we're done. In the latter case, including V gives a blue KT. And so that does it. Regardless of which of these two cases we're in, we've argued that there's always going to be a red KS or a blue KT. So this Ramsey number must be less than or equal to P, which is exactly what we have there. So that takes care of our proof. So let's take a moment to maybe focus on this result and which upper bounds we've already looked at that can actually follow from this. So in particular, the very first non-trivial Ramsey number that we looked at was R of 3, 3. And if you remember right, the argument was to say that we're looking at a case 6. We argued this was equal to 6, and we considered a case 6 and said, well, each one has to have at least 3 edges coming out that are all the same color. There's the red case. That proof is really similar to the case 1 we looked at. And there was the blue case. That was very similar to case 2 that we looked at. And in fact, we essentially just generalized that proof to all S and T. Because notice that what this result tells us is this is going to be less than or equal to r of 2, 3 plus r of 3, 2. R of 3, 2 is actually the same as R of 2, 3. Remember, we could switch the arguments. And both of these are equal to 3. So that actually proves our upper bound for us. We have a general result that gives us the same upper bound that we proved, focused just on that case. We could also take a look at something like R of 3, 4. Maybe this will give us the same upper bound here. Well, this one is going to be less than or equal to R of 2, 4 plus R of 3, 3. Well, this time I get a 4 and 6, and I get 10. Well, we actually proved that this was less than or equal to 9. And if you remember the proof of that one, we had 3 different cases. Two of the cases looked very similar to the types of cases that we've seen coming up in these proofs. But then there was that third case that we argued never actually happened because there was no graph that would have an odd number of odd degree vertices. That was our argument. So this one isn't quite as strong. We actually know this number is equal to 9, but our general upper bound only gives us 10. Not quite good enough. One other example that I encouraged you to take a look at the end of a previous video was R of 3, 5 to argue that this is less than or equal to 14. And if we were to apply Greenwood and Gleason's theorem to this one, well, here we have R of 2, 5 plus R of 3, 4. Well, R of 2, 5 is going to be 5. R of 3, 4, we know that that's actually 9. Now, if we were just using this bound, we would plug in 10. We've already proved that that's actually 9. There we go. We get 14 for this one. So that is the proof of our upper bound that I had mentioned trying to show in a previous video. One other comment that I should make about this theorem is that Greenwood and Gleason, they use this to argue that Ramsey numbers exist. So specifically, if you were to start with the case where S and T are both equal to 2, then use strong induction on the sum of S plus T, then you can argue that all Ramsey numbers exist. Basically, the fact that R of 2, 2 exists, you can argue that R of 3, 2 exists, then 3, 4, and you can basically run through all possible numbers to show that there is an upper bound for every Ramsey number. So as a corollary to this, you could state that all Ramsey numbers exist. All these classical ones exist. Greenwood and Gleason also proved another result where they strengthened this slightly in a certain case. So I'm going to just state this as a theorem, and I'll encourage you to try and prove this on your own. If you're unsuccessful, you might take a look at Greenwood and Gleason's paper. It's not a very difficult proof to go through, but it is kind of a variation of the result that we have up here. What it states is if R of S minus 1t and R of S t minus 1, the special case where they're both even, this is actually a strict inequality. You can prove a slightly stronger statement that they're never equal to each other. So R of ST is strictly less than the sum of these two. I'll encourage you to think a little bit about how that proof might go, but it's not a hard stretch from what we proved here. So the last thing I'm going to do in this video is let's take a little bit of time to focus on ways that you can go about generalizing these numbers. There hasn't been a whole lot of improvement on known classical Ramsey numbers in quite some time. It's very difficult. It's not easy to come up with proofs of what the exact values of these are. And when we only have maybe 10 numbers evaluated, it doesn't seem like we've gotten very far when there's infinitely many numbers that we could try to evaluate. So one direction a lot of mathematicians have gone in is trying to generalize these concepts. Let's come up with variations where maybe we can make a little more progress. Maybe some of that progress will then fall back on the classical numbers. Maybe it won't. You just have to see where it goes. Well, let me mention some of the different generalizations. These are all generalizations that I'm going to discuss a little bit in upcoming videos. The first generalization is one that Greenwood and Gleason actually considered. Namely, what happens if we use more than two colors? We typically use red and blue when we're thinking about a graph and its complement, which is kind of one way that you can define what a Ramsey number is. But from the perspective of how we've done it, where we take a complete graph and color all the edges, what's preventing us from using more than two colors? Nothing. And so we can define multicolor Ramsey numbers of, say, K1, K2, all the way down to K sub T. So here I would use T distinct colors. And then I'm saying, well, for any complete graphs and those colors that I have listed here, I'm trying to figure out how large of a complete graph I need such that when I T color it, I'm guaranteed to have a monochromatic complete graph of the appropriate order in the appropriate color. So it's a very simple definition to kind of extend from the two color case. A second class of generalizations was introduced in a collection of papers by Harari and Fatal, starting in 1972, I believe, or 71 is about when they started doing their work. And what they did is said, well, we're still going to color a complete graph, but maybe instead of looking for subgraphs that are complete, let's look for subgraphs that, might be something that's not complete, like a tree or a star. You can look at cycles. There's all kinds of variations. And so that was their generalization. They referred to these as generalized Ramsey numbers. So they looked at something R of, say, G1, G2, down to GT, where G sub I could be really any graph. And they were able to give some exact evaluations depending upon what the graphs were that were chosen. But in general, G1 through GT may not be complete. There's a third generalization that I won't get to until some later videos, but we can look at the case of hypergraphs. And typically whenever we focus on hypergraphs, we want a little more structure than just an arbitrary hypergraph. We want them to be uniform. And so what I mean whenever I talk about an R uniform hypergraph is that I'm looking at the edges as consisting of potentially more than two vertices, but all edges have the same number of vertices. So right now, when we talk about a graph, an edge is really just a set of two vertices. What if we consider an edge to be a set of three vertices, of four? Well, as long as we're consistent with what that particular order is for the set, that gives us an R uniform hypergraph. And the way these are usually written, we might write R of, say, H1, where H1 is some R uniform hypergraph, H2, all the way down to HT. And then typically there's a semicolon with a lowercase r here, where the lowercase r is just telling us what the uniformity is. So if we're actually focusing on a regular graph Ramsey number that's multicolor, I would just let R be 2, because graphs all have two vertices in every